So what is a vector? Remember, there are no wrong answers because all your answers will probably be wrong, unless you've been through this before, which is pretty awesome.
Something with magnitude and direction.
Exactly. So this is the old definition of vector. It is something with magnitude and direction. And that's a perfectly serviceable definition, to be honest, but we're gonna update it. So it turns out that this is really useful, and there may be some nuances of this definition that you really weren't battered with the first time you saw it. So a couple of, the first note is that, up to my ability to actually draw it, okay, these are actually the same vector because they have the same magnitude, at least, in my limited ability to draw them. They have the same length and they have the same direction, right? So this is actually, these are equivalent vectors. So there are three notes to make about vectors. First note is that vectors are translation invariant. Which kind of slangly, you could say that vectors are homeless, they're not rooted to a particular place. The difference in between the vector drawn on the left and its equivalent vector on the right is just I picked it up and I moved it around. Which means that when you see, for instance, a vector that comes out of the origin, that doesn't necessarily mean that it needs to be there, and you can move it as you wish. The second note is that and hopefully you guys never do this, but sometimes people is that it's just so useful to use components that we usually confuse a vector with its components. So we'll just call this vector v, for instance. This is also vector v. And I can write that vector v has component vx I hat plus vy j hat. Right? So this is kind of useful, and they give us precise numerical answers, but this isn't the vector. This is just what's called a particular representation of a vector. And it's not unique. In fact, a famous German or Swiss, I think he's German, mathematician named Hermann Weyl said that it's an act of violence to introduce numerical coordinates on a vector. So this is really the thing, right? This is God's honest truth. And in order to do calculations, we just happen to represent it with numbers. But never forget that this is really the thing. And as a final consequence of that is that all vector arithmetic and calculus, so all vector analysis has a geometric definition, right? And this is the part that kind of gets a little bit lost because components are so useful. So what really is, for instance, the definition of vector addition?
Putting one vector at the end of another vector and then seeing what the total vector is as a result.
Exactly, right? So, at some point you get so complacent with just adding them by adding their components, but this is hopefully what you were first given as a definition of vector addition. So I got one vector b and I'm adding it to vector a. And really, truly fundamentally, what the operation a plus b is putting them tail to tip, even though you have this, actually I'll save the mixed notation for a second, whoops. this is what you do 99.9% of the time, but this is, as file says, an act of violence, and you didn't need to do it. This is just a calculational expedient. So this is true for all of them. Okay, does anybody remember what the geometric definition of the cross product is? So we'll see how little review we need to do. Okay, so cross product will do. What about scalar multiplication?
That's just shrinking or growing the vector by some proportion.
Yes, right. So, we'll take a second if we need to, but all of these operations of vector analysis, and this is like the full list. So we have vector addition, vector subtraction. We have two flavors of multiplication. We have cross product and dot product. And then we also have, there's no like elegant way of writing it. We have scalar multiplication, which is scalar by vector. So all of these have a fundamentally geometric definition. We just happen to, use components as an expedient. Okay. So our first real topic in vector analysis, and why I've kind of belabored this point maybe more than I kind of needed to, is that we can choose different ways of representing the same vector. Any questions before I clear screen? Keep going. Cool. So we can choose different ways of representing the same vector, and what you guys have done in the past is you just got like really good at doing this. But probably haven't talked about the mathematical formalism of going specifically from one coordinate system to another. All right, so heaven help me, I'll try to draw this. So let's take an old mechanics problem. And here's your friend, a block on an inclined plane. And maybe you can get away with using the traditional XY coordinate system, but let's just really go nuts with this, and let's connect the block on an inclined plane to a spring, and then there's friction, and then there's a pulley with another block of some other mass, and then let's attach like a rocket to the back of it. Okay, and of course everybody should be able to draw the free body diagram of this really quickly. I've got tension. Depending on which way I'm pointing, I might have kinetic friction. Let's say we're going up the board. I've got this thrust force, Ft. You guys will learn about that finally in detail in classical mechanics. And then I've also got a normal force. And then I've got a spring force. Let's say it's pulling back. And then I've got this one weirdo weight. So clearly this like just really extreme example. If you guys use the XY coordinate system, how much the traditional one where I have vertical and horizontal X and Y, how much fun would your life be? Yeah, right. So pretty bad. What is, of course, the best coordinate system to use? And remember, all of these vectors, they exist independent of your choice of how to represent them. This is like the thing that's going on. We're at complete liberty to choose whatever coordinate system we want. And so really, what should I have as my x-axis?
The angle of the block.
Yeah, exactly. And then my, what I'll call y prime axis there. And how do I get in between my x prime and my y prime axis?
You calculate the projection of the vectors onto the new axis?
Yes. So you project new axis onto old axis, which sounds a little bit complicated. And you're right, that is the coordinate way of doing it. The geometric way of thinking about it is I just like rotate them. So our first topic in some sense is we're going to talk about how to relate different coordinate systems. And in fact, you're probably used to doing one but not the other of these things. So we'll restrict ourselves to this. We'll get into translations a little bit with the Christoffel symbol stuff, and I'll just point out why one might try to do this. So you're used to rotating coordinate systems. You just do it by staring at it in mechanics. We're going to talk about the fundamental math of rotations of coordinate systems. You can also have reflections. So for instance, those of us who are left-handed get sick of your right-handed coordinate systems, and we want to make our own crazy left-handed coordinate systems. So there's a way of doing that, and it shows up as a negative determinant in our transformation matrix in between one coordinate system and another. So we'll do these two things, just talk about the correct math of how I change from one basis to another basis. As kind of a side note, in general relativity, spelling is whatever you want it to be. Okay, this is one of those things that ultimately I'm gonna do a terrible job of trying to draw. This is not a bloodshot eyeball. This is like a black hole. We'll call it a black hole, okay? And what these represent is, for instance, if I were to like take a ball stationary at some distance r and I would drop it down into the black hole. You know, when you drop something, it goes vertically, right? And I take a neighboring ball and it also goes vertically. And you can see that their personally defined coordinate systems will they're not straight lines. So in curved coordinate systems, you really need to understand this math if you're ever going to access something that's not like flat. So this is basically the first step into general relativity. So and the point of this is that in general relativity in a curved spacetime, there is no single coordinate system that you could possibly use. So what you have to do is you have to have like local coordinate systems and kind of patch them together. So the idea of these rotation matrices and tensors will be the first step in doing that. Okay. So any questions before I clear that slide? Okay, so I will try to draw this as big as possible. I've got a coordinate system and I don't really, like it. So we'll just go through the plain old ordinary sines and cosines of how I turn it into a different one. So this would be my XY coordinate system, and my question is, how do I get it? I can never remember which way these arrows go. How do I get it into rotated? The reflected stuff you'll do as an exercise in the homework because it's just like kind of a realization into this coordinate system. We'll call this x prime, y prime, and we'll call the other one xy. And you know, all this stuff, we'll generalize it to 3D. My whiteboard is 2D, and also the math is easy in 2D, so we'll start with that as kind of a warm-up. What is the really like, you know, unless we do a reflection and I make the y-axis pointing downwards, which again, you guys will deal with on the homework, what is the one and only thing I need to know about my transformation in between the unprimed and primed coordinate system?
Angle, right?
Yeah, I just need like one real number because those are the same. So as kind of a side note, what you guys are assuming, because we're not complete weirdos and degenerates, is that we're rotating one basis into another. So what does basis mean? Do you guys get that in like linear or something like that?
Yeah, it's the number of different kind of basis vectors you need to like span whatever vector space you're in.
Yes. So it's got two properties. Basis for a coordinate system, I need a number of vectors, like the unit vectors, that is equivalent to the dimension of the basis set. So set of vectors, we'll call it unit vectors. So here we're in 2D. If we were in 3D, we would need 3 vectors. Okay, what else do they need to satisfy? Let's say I just picked 2 copies of the x-axis. And I said, well, I've got 2 unit vectors in 2D. So the thing that keeps me from expressing any vector with 2 copies of the x unit vector is that I need something that points in every direction. In fact, you need to be a little bit more kind of sharply worded than that, is that what needs to be true about these individual basis vectors?
You need to be able to make any other vector in the vector space with some linear combination of both of them.
Yes. Okay, and I'm not really like a linear algebra formal notation person. So, and this is actually how most physicists will talk about it, is that we will just say, and we'll get a little bit into it probably at the end of today in more detail. So this set of basis vectors needs to be orthonormal, which means each one is perpendicular to the other ones. Or orthogonal is the pretentious word for perpendicular. If you happen to be in like kind of a abstract space where it's not really like, you know, shouldn't be thinking about 90-degree angles or angles at all. Okay, so that turned into a longer aside, but really important. So what I couldn't do is I couldn't leave the y-axis alone and move the x-axis. So those actually would, you could represent any vector as a linear combination of x prime and y not primed. But what we want to do is you have to deal with some issues with like kind of overcounting and correcting. So a basis needs to be all right angles. So a set of unit vectors, all of which are at right angles. Okay. And don't worry, we'll get back into that if that seemed, I just like dislike words in physics classes, honestly. It's not why you guys are here. Okay, so again, this is the point, eyes on the prize. We've got a vector v. And the vector itself is the thing that exists in space and has a reality independent of the coordinates we choose. And the reason to choose coordinates is because they're useful. So the idea is that we have 2 ways of representing this. We have vx I hat, and it's got a y component j hat. And what we want is the second way. Call it v1 e1 hat. It's kind of clumsy notation, but I just want you guys to see how you'll usually be seeing unit vectors that aren't part of a specific useful coordinate system like radial, polar, or cylindrical. So this and this, no, that's the same v, it's the same vector. It just has 2 different coordinate representations. Okay. So part partly because this picture is going to get like super cluttered in a second, I will just do one of the components. But if you guys tell me how I find the components in the first place, I will tell you the relationship in between the x and y and 1 and 2 coordinates. So how, for instance, geometrically would I find Vx?
You can take the dot product with a unit vector in the x direction.
Yep. So this is going to be the component y. Yeah, I'll put that in quotes because it kind of isn't the component form if you just generically write the formula. So v dot I hat is Vx. And then likewise, if I wanted to find V1, I would take v dot E1 hat. So totally correct. Okay, how do I do that, at least on the picture? So I'm kind of suffering for not really knowing the component representations.
You just draw lines to the axes and see how much that is.
Yeah. So that, yeah, so what I was just trying to coax at is that is the geometric version of the dot product, is that if I wanted to find Vx, Vx is where along this copy of the real number line, the x-axis. You know, imagine that you shone a bright light from the top of, you know, perpendicular to the x-axis. Okay, it's not a great picture, but you know, hopefully you get the point. Is that this is the projection, or how long the shadow of V is on the x-axis, and then likewise here this would be Vy. Okay, that's a generic prescription, so that's how I would find V1 and V2. So I would project perpendicular to the x prime axis, and that this would be V1, and then I would project perpendicular to the y-axis, and this would be V2. So in some sense, what we've done with this particular set of rotation, or this rotation, is we changed our axes. We have a new basis that in that particular basis, V has more x component and less y component. And the matrix that we determined that performs this rotation will actually like reflect that. Okay. Okay, so that's what we're gonna do. I will draw the picture after erasing some of this. I know it's like kind of sloppy board work, so I'll give you guys a second. So what does this have to do with theta is the question. And there are two ways of seeing it. One is that this angle goes away. This angle goes to 0 and this angle goes to 0, so I could draw theta there. It's not going to be as useful as redrawing that slightly, which I'll do right now. If I just slide that projected angle down, I get a right triangle here. And what this is basically how much of what used to be Vx that I'm now turning into V1. So if you take this picture, and you squint at it, what you're left with is this equation. So I know that V1 is Vx cosine theta, and then Vy cosine theta. Right. So basically taking V1, which is right here, and the triangle looks a little bit backwards, but that just makes it easier for me to draw. So I'm taking the part of V1 that would project along the old x basis and pulling it off. That's the cosine piece. You can see it from this triangle. So removing the cosine piece. And then the sine piece is what gets projected onto Vy. And then likewise, I could see that V2, I don't know if it's too helpful to just like redraw the exact same geometry in a different picture, because I don't think these are particularly like clean pictures. You would see that you get a negative sign, it falls in the negative direction, and then Vy, oops, plus Vy cosine theta. Okay, this is kind of gross. Does anybody see what this thing actually is? So we've been kind of hinting and talking about linear algebra for a couple of minutes now.
It's a rotation matrix.
Exactly, right? So this is basically a multiplied out component form of this. V1, V2 is the following matrix multiplication. And then writing it really, really abstractly, which is where we're going to go pretty soon and stay there for the whole quarter, is I can express a change of basis into a new basis as V prime J. This is how I express a matrix multiplication. So here I'm going from 1 to 2. I got to go across both both columns. A, J, K, B, K. Right. So this is the VKs are the components of the old vector. The VJ primes are the components of the new vector. It's still the same vector. We're just changing how we represent it. And this thing is a rotation matrix. Okay. So everybody see, I left maybe some of the details off of how we got the second equation here, the V2. It's probably a really good exercise to draw something like this really big on your own and make sure that you see where this is coming from. So laboriously, we look at the geometry and we get these two equations, realize that it's a matrix equation, and then write it in kind of this bloodless component form of a matrix equation. Okay. That was 2D. Everybody should be able to, without any prompting, write down how I go from a basis to a different basis through a rotation in, I don't know, let's be string theorists, 10 dimensions. So just arbitrarily for some dimension D.
You would also have a rotation matrix, but it would just be, let's see, in 10D, will it be 10-dimensional, right?
Ta-da! See, wasn't that easy? Yeah, so that's the reason to abstract at this, kind of obnoxious level. In 2D, fine, do the work. And it's also good to have this example because we'll intuit some properties of rotation matrices. But this is, in general, what a rotation, you guys will do reflections on the homework. If I rotate from a vector from one basis into a new basis, which is just a rotation, it's just 10 by 10 if we're in 10 dimensions, or D by D matrix multiplication. Okay. And this thing, AJK. Okay, you can call it a rotation matrix. The individual components are called direction cosines. And as you guys can probably guess, both the rotation matrix and the direction cosines have a lot of properties that we'll kind of discuss in so far as if I start with a basis, I want to keep a basis. So I can't just write down any 10 by 10 matrix and say like, look, it's a rotation. But before doing that, let's see, any questions about this before I clear it? So to make Y a note about their, actually maybe you guys can tell me, why are we leaving out signs? Why are these called direction cosines? It's kind of a snotty answer, which is correct, and then there's also a non-snotty kind of trig identity answer, which is also correct. So you can actually express everything in this matrix, like even the off-diagonal ones, as cosines, just by kind of straightforward trig identities. Specifically the fact that, oops, sine of theta is equal to cosine of, negative cosine of theta plus pi over 2. So we could just call that cosine of pi over 2. You can express all of these as cosines generically. It's a little bit clumsier to write it like this, but if you're in 10D or you're asking a computer to do it, like who cares? Okay, so generically this is how we rotate. We have a matrix and we do matrix multiplication. Vector times matrix gives us new matrix. These things have properties. And the properties are dictated by the fact that we started with a basis, we really need to keep a basis. So one of the properties of basis vectors what happens if I take the dot product of x and y?
You'll get a scalar.
Yes.
Right.
And that scalar would be given by magnitude of the unit vector x, magnitude of the unit vector y, and the cosine of the angle in between them. Magnitude of x hat is 1, magnitude of y hat is 1. What's the angle in between them?
It's 90 degrees.
So I get 0. What's the scalar product of y hat with itself?
It's going to be 1.
What about, let's see how far we can jump. What about in our new basis, E, K, E, J, hats?
That one's also going to be 0.
Unless what one particular thing is true? Most of the
Unless
time, yes.
the bases aren't orthonormal.
So yeah, I should have written that. Yeah, I've got a good orthonormal basis.
Okay.
So it's true if K and J are not equal that they should be 0 if it's a good basis. So if J is not equal to K. What about, for instance, that?
If you're in a 1D system?
Yeah, or if it just so happens that, you know, so let's say that we're just in 3D and K could be 1, K could be 2, K could be 3. Likewise, J could be 1, J could be 2, J could be 3. If J is 2 and K is 3, I should get 0. If K is 1 and J is 3, I should get 0. But what if K and J are both 1? I should get
1.
Yep. So if J equals K, I should get 1. And honestly, this is just like notation. At some point, everything about this weird basis vector notation clicks. But what I have is K and J could be 1 all the way out to, you know, if I'm in 10D or whatever D. If these two bases, if these two labels are not equal, it would be like having the z-axis and the x-axis. They're perpendicular, their dot product should be 0. If they are equal, it would be like the dot product of one basis vector with itself, x with x or y with y or z with z, and I should get 1. Okay. There's a lot of basis vector stuff and a lot of linear algebra out there in this world. So it would be really cool if we had an elegant way of describing this property. Does anybody know the elegant way of describing this property?
Is the Kronecker delta?
Yes. What's technically called the Kronecker delta symbol because it's not a function. So what we're going to do is here. K-R-O-E-N. Kronecker. You're just like, you're super showing off how like erudite and pretentious you are if you remember to call it the Kronecker delta symbol. Okay, never call it a function, always call it a symbol. You get like so much cred in physics circles. Okay, so we're going to define this thing basically to keep me from having to write all of this crap over and over and over and over. So lowercase delta jk is equal to 0 if k and j are not equal, and it's equal to 1 if k equals j. So now what we have is, after, remember how much crap I had to write to describe what a basis set is? So now what I can do is I can just say, like, you know, a set of d vectors in a d-dimensional space, you know, 2 if there are 2, makes a basis if their dot product is equal to the Kronecker delta. So this is like really concise. Okay. So question? Okay, so we'll can all of this, we work for it, and we will just say following this. So for basis vectors, oops. It's just bad table manners to call it djk versus dkj, but I won't do that. So it's the same, it's symmetric. Okay. Ta-da! So this is what it means to have a basis. So there's all this stuff that you guys probably learn, you know, in the beginning of linear algebra about representing a vector, any vector at all in the space, or spanning a space. This is what physicists who are ultimately like fairly practical people, believe it or not, at least by mathematician standards, this is what we distill having an orthonormal basis into. If I'm in a d-dimensional space, I got d of them, and they satisfy dot product equals Kronecker delta. Okay. So if you have a basis that does this, you can represent any vector you want. Pick the basis you want that's very useful, and make sure that it does this. Okay, so any questions about that? Okay, so all of this is a preamble to the following. I have this rotation matrix, and if I have a basis that goes into it, I really hope that I get a basis out of it. And that means that the Aij or AJK, however you want to call it, has the following mathematical property. And the good news is I will not ask you to verify this by hand for anything bigger than 3D. But if you are a string theorist, not like string theorists actually do kinematics problems in real coordinate systems, but if you were in 11D or whatever, this would also be true. I would just go from 1 to 11. Okay, there's an alternate way of writing the exact same thing. And just be aware that you'll see this. It is literally the same thing. So this little, it's literally a T. Later in your life, you'll get to like daggers and bolded daggers in quantum mechanics, but that's just T for transpose. Is it worth a reminder about what the transpose of a matrix is?
Flip along the main diagonal.
Exactly, right? So let's say I have, let's see if I can actually do this without thinking too much. Maybe I have a good example somewhere. Sure. Okay, this is an obnoxious example. What's the transpose of this matrix? I just picked it out of the notes without thinking.
It's the same.
Yeah, so I would flip these two off diagonal components. So the 1-2 component would become the 2-1 component. So this is what's called a symmetric matrix because it's got the, its transpose is equal to itself. Okay. But yeah, flip across the diagonal. So for example, A32 would become equal to A23. I'll write that correctly. Okay, so this is, any questions about all of that so far? So I'm going to say something that for you guys is going to be mostly notation, and it's notation that you'll see a lot of places, and it will be really damn confusing until, you know, maybe at some point in your life you do some curved space-time or manifold stuff or differential geometry, is that there are two ways of creating rotation matrices. We'll basically talk about their generic properties and we'll do it by hand. There is another way of creating them, is that if, for instance, you have two different coordinate systems, this is mostly notation. So you got two different coordinate systems, and basically like the most important vector in a that you'll consider actually is the position vector. So I've got coordinate system number 1, and R is R of X, Y, and Z. And I'll put, actually, let me put subscripts on those so notation doesn't look super weird. In system 1, I keep track of X1, Y1, and Z1. Okay. And that would mean that this has, for instance, Rx, X1 hat, Ry, 1, and I will stop doing this really quickly just so you see how gross notation might be. Z1, Z1 hat, ew. But we'll just say that, you know, it's a vector, it's got 3 components in some particular coordinate system. And then I've got a second system. Same exact vector, but now I'm describing it in terms of x2, y2, z2. So, you know, again, literally the same vector. So we'll just say direction cosines. So one way of actually creating these, which we won't really do because it's kind of an advanced topic, is looking at the rate of change in between different basis vectors. And you'll see this denoted 2 different ways. One with this kind of grubby notation, where one is the old axis, the other one is the new axis. But I'll just give you an example of what this means and then do a little bit of like geometric hand waving about why this is, you'll see this. This doesn't necessarily mean that you are being asked to do differential calculus. You'll just see like on, you know, Wolfram's Math World or something like that, you'll see this notation for rotation matrix. And you're like, what the hell is calculus doing in my rotation matrix? So it turns out that if you actually had a complete coordinate system, you could just take partial derivatives and generate these rotations. So what this means, for example, in this case, is that for our system, if I wanted to find the 2-3 rotation matrix, I would look at the new axes. I'm rotating from system 1 into system 2. So I would look at the new system, that's 2. So that would be the second element. So that would be dy2. And then it came from, so how much of the old third basis goes into the new second basis element? So that would be dz1. So what on earth does rotating have to do with calculus? Well, if you kind of imagine grid lines, so here's my old basis, and here's my new basis. And let's get crazy, let's make this angle go below the axis. So if you think about it, the lines, or the axes x and y prime, they're actually kind of equivalently lines of constant blah, blah, blah. So the lines of constant x prime look like these, I don't know, was that fuchsia? And the lines of constant y look like these. And so if you're asking how this line changes with respect to x, you're asking the slope of that line. The slope of that line is the angle. So, you know, for us, we won't do anything like really weird, like curved coordinate systems for a while, but you'll see this notation and it'll be like kind of baffling. And, you know, at this point, you've been trained to see these squiggly Ds and say like, calculus, I've got to take derivatives. For you guys right now, until we get into Christoffel symbols, it is just notation. But it's notation that says that the rate of change of a line of constant y prime has something to do with the rate of change of y. And the slope of that, you know, as per what differential calculus means, actually really is cosine of theta. So this really is a direction cosine. Okay, but don't freak out when you see this. All it is for you guys right now notation. Okay, any questions about all of that? Don't worry, we're going to actually do some stuff that involves calculating things and return to normalcy instead of this like philosophical discussion shortly. Okay. So, as promised, we now have our new definition of a vector. And this is the one that you guys can stick with for the rest of your lives. Is that a vector is anything that transforms like a vector. Which means there's a lot of stuff that you maybe didn't think about as vectors that are actually vectors. So for instance, things that look like calculus operators that are looking for a function to act on, they can be considered to be vectors because they transform appropriately. So what that means is I've got a thing, call it, I don't know, V because I'm like really uncreative. If V prime K equals V, let's do J from 1 to N. We're in N dimensions. Okay, so that would be like pretty unfulfilling if we didn't talk about two things that used to not be a vector and is now a vector, and one thing that used to be a vector, even though you were told probably not to consider it as a vector, that is not a vector. So can anybody name anything that seems like it should be a vector that is not a vector? I can think of two actually. And this definition would suss that out, but the old definition of just magnitude and direction would not. So something that has direction and magnitude
just a point on a number line, right? Or I guess would that count as a vector under our old definition too?
It depends on how you made it.
Okay.
So if you're talking about just a position vector going from the origin to the point, then no. But if you're talking about two cases, so one might be geometric, the other one is like kind of dorky and mathematical. So think about like a crack in a rock. Does that have a magnitude? And it can be specified by 2 points, yeah. Does it have a direction? I don't know. I mean, it's pointing northeast, I guess. So something like this is technically what's called an axial vector. If you turn it by 180 degrees, you get the thing back. And that wouldn't show up in this definition of vector. You'd need to turn it by 360 degrees to get a true vector back, i.e. one that has a head and a tail. So so-called axial vectors are not vectors, and this definition would find them. There's another thing that seems like a vector but isn't a vector. Let's say I created something through a cross product. So you can kind of figure this out geometrically too, is, you know, the right-hand rule definition of how you get something through a cross product. Okay, so these actually also don't have the correct transformation properties. Whereas if you flip both of them, that's a rotation. That's a rotation by 180 degrees. But you end up with the vector pointing in the opposite direction. So this is what's called a pseudo vector. So if I have A pointing that way and B pointing that way, A cross B would point up. And then if I flip them both, I would get this pointing down, but that's just a 180 degree rotation. Or if I flipped one of the axes. And then finally, there will be things that look like vectors, don't look like vectors, but will actually be vectors. So for instance, this thing, d by dx, I hat plus, should put the I hat on the other side. So differential operators, something that, you know, has no business seeming like a vector, actually transform in the appropriate way. So those will be vectors as well. So any questions about any of that stuff before we go through an actual example with actual numbers that are actually useful? Okay. Just to be like really picky, got a vector A. It's a mess.
Is that -1/2?
It is.
Okay.
Every time I try to erase it, it erases the background text. But yeah, that is supposed to be -1/2. And then √3/2. Let's see if we can do better here. So question 1, kind of definitional. Question 2, basically we did a lot of talking about why you would care about this thing and what it's supposed to mean, but we didn't talk about how you're supposed to find it. In fact, we even talked about how you're not supposed to find it by taking spooky partial derivatives in between perfectly expressed coordinate systems. I'll probably put a note on the video, but I think just kind of thinking back 5 minutes ago, to be clear, the pseudo vector thing has to do with a property of the rotation matrix or the direction cosine matrix that we haven't talked about in detail yet, which is reflections. I don't know if I said that at the time. Is everybody done with the first problem? Is it a basis?
Yes.
Yes. So what did you need to check to determine that it was a basis?
The two things were that they're orthonormal and unit length.
Yes, right. So we had to check that, let's do the fun one first, a dot b has to be equal to 0. So basically, generically, if I have a basis, it's got to be ek ej is Kronecker delta jk. So dot product the thing with itself, you should get 1. If you dot product it with the other thing, you should get 0. And I'll use the mathematician notation. I'm fine with you guys doing this. The reason physicists frown upon this is because in quantum mechanics, the angle brackets are reserved for something really important and ubiquitous. So it just gets like kind of confusing. But if you guys do this all quarter, I'm fine with it. So match the components, I get minus 3/4 x and x plus positive 3/4, √3/4, sorry, and that's 0. So dot one with the other, I get 0, whereas if I dot the thing with itself, I get 1/4 plus 3/4. Which is 1. And when I dot B with B, oops, that's A with A. Yeah. I also get 3/4 plus 1/4. So yeah, it's a basis. Any questions about that? Okay, so what that means is I can kind of promote them to basis vectors, and henceforth I will say that E1 hat is A. So we'll give it a hat, so you're basically saving people some work and they don't have to check themselves that they're unit vectors, and E2 is B. So now defined as such. Okay, what about question 2? You guys want more time with that?
I'm about done.
Okay. Okay. So you may have done this differently, but I will do this in the way that kind of explains, if it's not already clear, why these are called direction cosines. And essentially we made that 2D transformation matrix for that 2D rotation laboriously by hand. And in fact, we kind of skipped a little bit, and maybe you'll see why, because it's a little bit misleading. So generically, if I want to look at how much one thing projects along another thing, that's what the dot product does. So if I've got a vector P and a vector Q, is that essentially, and they're separated by some angle theta, up to their individual lengths as scale, the essence of the scalar product is how much of P falls along Q. That's kind of the geometric meaning. So that's P, Q, cosine of the angle in between them. Now, if P and Q happen to be normalized, what am I left with? I.e. their lengths are 1. All I've got is the cosine part. So if I want to know how much of my old basis falls along my new basis, all I have to do is look at the dot products in between them. So if I want to know how much of E1 falls along the old x-axis, denoted by I hat, I just have to look at the dot product in between them, because both of their norms are 1, so I get 1 times 1 times cosine in between them. Okay. So the question is, what does I hat look like in its own basis? So then I already know what E1 and E2 look like in this basis that were given to me. What does I look like in this basis? I hat. And for that matter, J hat. Sometimes the simplest questions are the most difficult.
The question asks about a traditional axis, so it's just I hat could be 1, 0.
Exactly. All x, no y, right? And it's 1 unit long. And likewise, J points along the y-axis, so it's all y, no x, and it's 1 unit long. So, ta-da. So this is what this means geometrically, but we've got components after the long finger wagging warning about taking components too seriously, and you can use different bases. We'll do exactly that. We'll use components. So E1 dot I is -1/2 √3/2 dot product 1, 0, which just picks out the first component. So that's -1/2. Okay. So this is the 1, 1 component of the direction cosine matrix. So old basis 1, new basis 1. And then likewise, E1.j, which would be -1/2 √3/2 dot 0, 1, picking up the second component, √3/2. That would be new basis 1, old basis 2, so that would be A1, 2. And then let me just clear all this stuff out. You guys okay with me clearing screen? Okay. So finally what I get is this. I get a rotation matrix that looks like this. E1.I, E1.j, hat, E2 dot I hat, and E2 dot j hat, which is, and you can see where that really lame example that we used for transpose came from 2 pages later in my notes. This is a symmetric matrix. And what you could do is, and maybe remind yourself, even though, you know, it should look suspiciously like a calculation you did in part 1 of the problem, is that you can check that Aij, A, K, I is the Kronecker delta function, which is to say matrix multiply this thing by its transpose. But what is matrix multiplying this thing by its transpose? That's exactly the dot products that you guys were doing. You'll dot product, this is essentially the vector A, and this is essentially the vector B, right? You'll dot product A with A, B with B, and A with B, and B with A, which will give you nothing but 1s and 0s. You already checked that. So essentially, you know, a nice 2x2 example that's not too laborious. This is what all this stuff means. And the nice thing about this notation and these formulas is they'll go into like 3D and 4D where, you know, you can't just squint at 2 axes and write down sines and cosines. Okay. So why are we doing this? This was the original question that we started this whole thing with. Okay, there's a smarter way of writing that, I think. So I've got a vector and it's expressed in the xy basis. So we'll call it C and call it minus 1/2, 3/2. I can't trick you guys with that, so I'll just flip the signs. So how do I get this from old basis to new basis? This is what I labor to produce. I just multiply it through my matrix, right? And I'll do it in the kind of coordinate-free way, is AC equals C expressed in terms of new coordinates. And then tell me what that is, and then tell me that you're not surprised by it.
-1, 0.
Exactly. What does that mean about C? What is C? So here in the old coordinate system, so I don't know, I feel like because the numbers, you just have like this set of 2 numbers. And before we get into specific coordinate systems, it kind of gets confusing about what is actually going on. Is that imagine that we just like removed all of the door, like all of the addresses from every single street and building in Seattle, and then came up with a new scheme, right? It would still be true that every street address has like a number and a street, but all those numbers would be different. It's the same place. But what you would have is just, like another 4 or 5 digit number, 3-digit number. So this is still, so this is C. It is the exact same vector. It's just expressed in the old numbering scheme of old x coordinate, old y coordinate. This is also C, but it's expressed in the new coordinate system. So that's all that's going on again. So different active violence, it's literally the same vector. It's just did you use the tilted coordinates or untilted coordinates. Okay, so what we're gonna do, and I'll just, we'll do this as a warm-up with the cross product a little bit. Maybe I'll leave that for a homework problem. Sort of as intuition, you should have this list that's either, probably already halfway there. And we have enough time to do the scalar product, so we'll do the scalar product. So I'm afraid of your new coordinate system. I don't like change. I don't trust you guys. I don't want to use it. I compute the scalar product of two vectors P and Q in the old X and Y system. And you guys love your new coordinate system. You worked really hard on it. You're really proud of it. You compute P dot Q in the new coordinate system. What's going to be true?
The scalar product should be the same, right?
Exactly. And the reason for that, and the reason we talked a bit about like why all of these things are defined geometrically and in a coordinate-free way, is that this shouldn't depend on your accounting scheme, right? So this should be independent of coordinates. And to be honest, if you're doing something that is coordinate dependent, it depends on your personal choice of coordinate system, it's not physics, right? So there are no X and Y axes out there in the real world. It's all like a fictitious, whatever. So if you notice, velocity is a coordinate-free thing. You subtract the beginning and the ending position, and so your choice of what 0 is independent. Okay. So now we have the technology to prove it. And I just want to put this up, and I'll go kind of fast, as this is kind of the style of something that you guys might be asked to do. Okay, so let's just take P and Q in our new coordinate system. And basically, I want to start here and end here. So how is it that I express P prime and Q prime in terms of P and Q? And let's just be reasonable and keep it to 3D. Oops. So this is what the scalar product means in a coordinate system. Shame on me for using it, but we have to for this proof. So I match the 1 and 1 and the 2 and 2 and the 3 and 3. But now how do I turn the P prime and the Q prime back into P and Q? How do I get from one coordinate system to a different one? I use
The rotation matrix.
exactly. So J from 1 to 3, A, JK, P, oops, J, and then I from 1 to 3. So the primed are really just, I took the original vectors and I pumped them through my rotation matrix. And there should be JK, sorry. Okay, and then this is just a collection of sums. I can move the sums out and rearrange some stuff. So really nasty, but K, J, I. If only we had a nicer way of doing summations like this, which we will. P, J, Q, I, and then A, K, J, A, K, I. So what's the point of me rearranging stuff like this? Does this look kind of suspicious to anybody?
It's going to be 0 if they're orthogonal, right?
Yes.
Yeah.
Two things can happen. Either the indices don't match or the indices do match. But what's going to happen from like kind of a sociological level is you guys are going to flip back through your notes and know that there are going to be properties of these matrices. And in particular, when I sum these over the repeated index, the K index, so I'm just left with I and J, I'm going to be left with the Kronecker delta symbol. So 2 pages back in notes, I have a property of this matrix that lets me do something magical. Replace it by Ji. And believe it or not, this is just an alternate representation of the dot product. Because if I sum over J, this is 0 when they're not equal. J and I are not equal. And it's 1 when they are equal. So this is actually equal to sum over J, Pj, Qj, which is exactly equal to P dot Q. Okay, so that was kind of there for stylistic reasons. This is kind of the idea of what we'll be using some of the technology we develop in this class for. Is there will be these like kind of long fibrous things and proofs. And basically what you do is know where you're supposed to start, know where you're supposed to end, and then flip back through and realize that some of these objects have particular mathematical properties. In this case, I use this Kronecker delta identity. If it's the first time you've seen it, don't worry, it's not the last time you're going to see it. Sorry, I forgot the most important part of the proof. We'll fill in box, or I type QED or something really. QD, I think, is the most pretentious way of doing it, so I prefer that. Okay, so where you guys are at with the homework is you can probably do a lot of the problems that are not from the book, the ones that I wrote, which are about transformation matrices, and then probably start the first book problem. I'll open a discussion board. We'll start class with any questions on the homework. Again, if they're going to be kind of gritty recorded lectures, we'll have lots of time in class to work on them. Okay. I'll stick around for a few minutes if people have additional questions, but otherwise I will see you guys on next Tuesday.
So what is it, just for clarification, that you want us to have complete by class next week?
So what might happen is I haven't looked too deeply into the notes, but like, okay, this is the limit of like a 4-minute example proof that I'm willing to put on the whiteboard thing, because you guys watching this through like, I don't know, like somebody shouting mathematical proofs through Burger King drive-through is just like not okay. So if something's like really, really intense, I'm just going to record that lecture on a whiteboard and then post it a priori. So when we solve differential equations in radial coordinate systems and stuff like that, I'll record those with at least 3 or 4 days notice and then post them and let you guys know that we'll talk about it in lecture.
Okay.
But for now, we're just doing some vector arithmetic and transformations. So I don't think this is too bad, but you guys let me know if like this is unreadable and painful, and we'll put that up on the board.
Thank you.
Yep.
Thank you. Yeah.
Thanks.